All right. So last time we have seen the construction and the basic operation of the enhancement MOSFET. Why it is called enhancement MOSFET? Because see, we already don't have a channel over here to begin with. Okay, just like D MOSFET, we don't have, or rather, in contrast with the D MOSFET, we don't have the N-type channel here, and the channel is induced, or this particular section. Okay, this particular section we are actually enhancing. Okay, because of the application of the gate to source voltage, and because of that we are creating a channel there. Okay, and that is why the name is enhancement type MOSFET. Okay, we also saw that the N channel is induced. I mean, that is what I have already told you. After a certain value of VGS, that is after you start increasing VGS, ID starts, significant value of ID starts flowing. Now, interestingly, if you look at the characteristics of the E MOSFET, let me just pull the figure. So here is the characteristics. Now look at the characteristics carefully. What you see here, we actually have two characteristics laid side by side, and those are the input characteristics. No, let us not say it is the input characteristics. These are the transfer characteristics. So these are the transfer characteristics, and these are the output characteristics, also called as the drain characteristics. So if you see carefully, I have drawn ID versus VGS, just like what we did in case of E MOSFET and rather D MOSFET, and also as in case of the JFET. Okay, and this is essentially ID versus VDS. Okay, so what do you see from here is that again, as I start increasing the value of, let us have a look at the output characteristics to begin with. So just like JFET, whenever the VGS is below this VT, now for example, I have considered a typical example of a MOSFET which is having VT, that is a threshold voltage, which is also called as VGS EH, okay, which is given in the data sheet to be equal to, let us say, 2 volts. Okay, so below 2 volts, there is no drain current flow. Why? Because there is no channel which is induced and there is no drain current over there. Now, as I go on increasing the value of VGS, as you can see after this value of VT here, okay, the drain current starts increasing. So as I keep VGS constant at, let us say, 3 volts here, I keep VGS constant at 3 volts and I start increasing VDS, and I start plotting, or let us say measuring the value of ID. So as you can see here that this particular, if you look at this curve, which I am highlighting right now, okay, this is what is happening. So if I go on increasing the value of VDS, you can see that the ID value increases right from 0. It increases right from 0 over here, and it follows this curve. Rather, we are getting curve like this. Similarly, if I keep VGS constant at 4 volts, I'll get this kind of curve. Again, you can see that after a certain value of VDS, ID remains fairly constant. Again, this is because of the pinch off effect. Okay, we have already seen the pinch off effect when we studied the FET, but pinch off here is slightly different. Okay, and what is that pinch off effect? We are going to see that. what happens is actually something like this. So let me just pull another figure. Okay, so as I increase the value of VDS, keeping VGS constant, so this is constant, and I go on increasing VDS. Okay, what happens is the pinch off or the pinch off effect is observed for the channel like this. So the channel width does not remain constant and it actually narrows down. Why does it do that? Okay, so let us see why it does that. So if VGS is fixed at some value, if VGS is fixed at some value, guys, am I audible?
Yes, sir.
Okay. Again, as you can see here, that we have a representation of this. Um, we have a representation of this channel in terms of the resistance that is offered by the N channel, which is created. So it will be better if I put another figure here. Okay. So as you can see that this is as if there is a resistance here, right? Agree to that? You all agree to that?
Yes, sir.
Okay. Now, as I go on increasing the value of VDS, see what is happening. The voltage here will be different. The voltage here will be different. Again, similar. Do you recall the similar kind of situation we had in case of the JFET? Like here, it was, why the shape of this was like this, and then, okay, you remember this?
Yes, sir.
So along, let me put some other color here, and then it was increasing like this. And why it was having a peculiar shape? Because the voltage along this particular channel, this was VA, then this was VB, and this was VC. A similar kind of phenomenon exists over here. Okay. So if
Yes.
VGS is fixed at some value, let us say, okay, first of all, what we are going to do is we are going to apply KVL to the terminal voltage of this MOSFET, meaning that your VDG. So what is this VDG? What is this VDG? That is the voltage between these two terminals. Okay. How are we going to get that? VDG will be equal to VDS minus VGS. Simple. Look at this channel. Look at this channel over here. Okay. This is with respect to ground. Okay. So this is ground. No problem with that. VGS, that is with respect to ground. And then what we have here is that we are applying VGS here and we are applying VDS here between drain and source. So this is between drain, this is between drain and source. This is between gate and source. So whatever is left can be found out VDG, voltage between the drain and the gate, as VDS minus VGS. Are you able to understand this equation?
सर नहीं, ये इक्वेशन नहीं आ रहा.
Okay,
आप कोई
ठीक है, ठीक है.
डायग्राम बना सकते हैं?
ठीक है. Okay. So let us say I'm having this as the this as the drain.
Sir, you're not audible.
This is going to be, what is this voltage going to be? This is going to be VDS. समझ में आ रहा है? Hello? Am I audible?
सर एक्चुअली आप डिस्कनेक्ट हो गए थे कुछ
और
सेकंड.
ठीक है ना, तो मैंने ज्यादा कुछ नहीं बोला है. तो ये वोल्टेज क्या है? ये अप्लाई किया समझो, ये है VDS. ये दो पॉइंट के बीच में अप्लाई कर रहा हूं मैं वोल्टेज, बाकी कुछ नहीं है. ठीक है, जस्ट डू अवे विद दिस फॉर क्लैरिटी. So ये voltage क्या है? Voltage between this point and this point is VDS. Now voltage between this point and this point, ये क्या है?
So VGS.
VGS. So what is the voltage between this point and this point? That is VDG.
Yes, sir.
So how do you find out VDG?
So VDS
It's
minus
VDS
VGS.
minus VGS. That's it. This is that
Yes,
equation.
sir.
Got it now?
Yes, sir.
Okay. Now let us say that your VGS is fixed at some value. We'll take some numerical value here. Let us say VGS is fixed at VGS is fixed at some value, say 8 volts, and VDS is increased. So VDS is increased from, let us say, 2 volts to 5 volts. Now this is interesting. So here VDG, what will be the value of VDG? From this equation, what is the value of VDG? VDS minus VGS, right?
Yes, sir.
Okay. So earlier we had VDS as 2 volts and VGS as 8 volts. That gives me minus 6 volts. All right. And in
Yes,
second
sir.
case, it will be 5 volts minus 8 volts. That gives me minus 3 volts. Now this is just for your understanding, huh? This figure. Otherwise,
Yes,
don't
sir.
get confused. So VDG is effectively what? It is negative in this case. So if such is the case, that is the voltage VDG, so voltage VDG will increase from minus 6 volts to minus 3 volts. Increase क्यों बोल रहा हूँ? Because it is going positive. So minus 3 volt is more positive than minus 6 volts, ना? Positive बोल रहा हूँ मैं.
Yes, sir.
Yes, sir.
This I have to understand properly. So gate will become less and less positive. So this gate, so this is the gate terminal. So gate will become, so I'll write it down. Gate will become less and less positive with respect to drain. So with VDG as minus 6 volts means gate is plus 6 volts higher than drain. ये बात समझ में आ रही है? ये क्या है? वोल्टेज बिटवीन ड्रेन एंड गेट. ओके.
Yes,
So
sir.
VDG 6 volts है, minus 6 volts है, means you can call it the other way around, that the gate is plus 6 volts higher than the drain. बराबर है? समझ में आ रहा है कि नहीं आ रहा है?
Yes, sir.
All of you? Only one positive answer I'm getting.
Yes, sir.
So अभी next case में when VDG is minus 3 volts means what? Means again same, gate is plus 3 volts higher than drain. So what do you see from here? What we see is that the gate is becoming less and less positive with respect to drain. समझ में आ रही है बात?
Yes, sir.
So now gate is less positive with respect to drain. Let us see Let us understand this first. This reduction in gate to drain voltage will reduce the attractive forces for the free carriers in this region of induced uh, channel. So putting it in this way, so अभी ये क्या हो रहा है? So मेरा गेट ये ड्रेन से और कम 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 पॉजिटिव होते जा रहा है, लेकिन अपना बेसिक अंडरस्टैंडिंग क्या है कि गेट अगर पॉजिटिव है, बात समझ लो, गेट अगर पॉजिटिव है तो यहाँ पे इलेक्ट्रॉन्स इंड्यूस होने वाले हैं, है ना? यहाँ पे इलेक्ट्रॉन्स इंड्यूस होने वाले हैं, चैनल तैयार हो रहा है एंड दैट सॉर्ट ऑफ थिंग, राइट गाइस? हेलो,
Yes, sir.
Yes, sir.
तो हमने क्या बोला है? Because of this gate becoming positive, more number, this gate is more positive, more number of electrons will be attracted here from the p-type region and you get a formation of the channel. Now the problem here is the phenomenon over here is that the gate is becoming less and less positive with respect to drain if I increase VDS. So what is going to happen to the channel width? Earlier the channel was very good like this, but because this is becoming less and less positive, यहाँ पे क्या होने वाला है? ये चैनल का विड्थ जो है ये ऐसे कम होते जाएगा. So this will be the effective channel width. I mean, this is how it will form. It will start becoming like this. Earlier it was like this. ये बात समझ लो. ये क्यों हो रहा है? ये phenomenon क्यों हो रहा है? ये tapering क्यों हो रहा है? Because gate is becoming less and less positive with respect to drain. मैंने जो अभी बोला, समझ में आ रहा है?
Yes, sir.
So this causes the effective reduction in the channel width, or this causes the reduction in the effective channel width, putting it the other way around. Eventually, the channel will be reduced to the point of pinch off and saturation condition is established. So, putting it like this here, I will say that as I go on increasing VDS increase करना बोले तो क्या कर रहा हूँ? VDG वैल्यू कम 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 होते जा रहा है, ठीक है ना? तो ये चैनल जो है, दिस चैनल will start becoming more and more narrower. So as I go on increasing the drain source voltage, this channel earlier, let us say it was like this, then it started narrowing down, like this and like this. तो ये और नैरो होते जा रहा है. So ये चैनल विड्थ जो है ये रिड्यूस हो रही है. That is because we have already seen the phenomenon why it happens. All right. So at a certain point, what we have is, but it cannot reduce below a certain, let us say it will not become like this. No ways. So it will stay like this, for example. Oh, let us not clutter the figure. ये फाइनल वैल्यू ये हो गया सब, ये हो गया, ठीक है? अब आप बोलोगे ड्रेन करंट कैसे फ्लो रहा है? Should be the question that is to be asked by you. So the answer to that is, basically what we have is a very large voltage difference or electric field. Let us say this value, this width is very small, very small, or the voltage difference at this point and this point, that is the boundary, is comparatively large. So electric field बहुत ज़्यादा होगा. Electric field कैसे होता है? How do you define electric field? What is the unit of electric field, by the way? Volts per meter, no? Guys?
Yes, sir.
So if this distance is small and electric field is comparatively larger, what will happen to the electric field? This voltage is small, large and the distance is small. What will happen to the electric field? It will be very, very large. है ना?
Yes, sir.
So yeah, because of this very large electric field, the electrons which are coming over here, they are drawn into, let me declutter this. So they will be drawn, the electrons which come over here, they will be drawn into this region because of this very high electric field. And still your drain current is going to flow. But the drain current is not going to increase further even if you increase the value of VDS. This is the pinch off phenomenon in the MOSFET. अपना जेफेट का पिंच ऑफ अलग था थोड़ा सा, ये थोड़ा सा अलग है. So for example, if you look at the characteristics, going back to the characteristics, you'll see that the drain current does not increase further. So if you take this one for example, see the drain current does not increase further. After this certain point, it will stay constant even if you increase VDS. This is because of the pinch off phenomenon. All right. And how do we get the characteristics then? We get the characteristics like this. If you look at the transfer characteristics, that is ID versus VGS, you'll see that up to a certain point, the drain current is 0. This point, which we call as VTH, and then the drain current increases. And but do you again see that what is the relationship between? I mean, is it linear? Is this?
No,
Is
sir.
this? It is. So it is again non-linear. So MOSFET is again a non-linear device. Okay. And the drain current is related. The drain current is related as K into VGS minus VT bracket square. ये है उसका relationship between the drain current and the gate source voltage. So this describes the transfer characteristics. Now you can find out K, which is a constant from the data sheet. ID on, that is the drain on current, is given in the data sheet. VGS, you're going to get an assignment based on the data sheet, so don't worry about that. VT bracket square, just a modification of this equation. So you can get K from the data sheet. ID on is given, VGS on is given, VT is given. So you can get this K from this equation. Okay. So again, there are various different regions in this characteristics. If you look at it here, so if I just plot this thing down, for example, for a particular curve, you can say that this is called as the triode region. Again, this is called as the saturation region. Okay. Now यहाँ पे again the slope, ये जो slope है, ये कर्व का स्लोप जो है, ओके, which is called as GDS, which is the transconductance. It's the output conductance, which is 1 by RDS in the triode region. और यहाँ पे इसका स्लोप अलग हो गया, तो इसको बोलते हैं 1 by RD. Just remember this. Okay. Let us have a look at the P channel. N channel तो देख लिया हमने. Let's see if I have a P channel. Okay. So P channel, E Mosfet characteristics. See what is the difference? These are all negative values here, and so till your VGS is minus 2 volts, it doesn't conduct. Above that, like that is if you go increasing VGS in the negative direction, your drain current will start flowing. So this is your P channel MOSFET characteristics. Let us have a look at the symbol quickly. For N channel, you have this symbol. This is slightly complicated symbol. This is your gate, this is your drain, this is your source, and this is your substrate or body. Okay. For P channel, drain, source, gate, substrate. Now there are alternative symbols being used by people, so I'll give you those also. So again, this is drain, source, and gate. Now, what is the difference between this earlier symbol and this symbol? This is the upper one is for 4-terminal device where the source of the body is available, and the lower one is for what?
Three
The
terminal.
3-terminal.
Three
Right?
terminal. So you are not audible.
This is your drain and this is the source. This is for N channel. I am writing this. Here it will be like this. This is much easier to remember. Just remember this is source now and this is drain and this is gate. I prefer this. Easier to draw. Now, many times this VGS minus VT, this component is very important. Huh? Please remember one thing. Take you to a little bit depth of this, so that you'll be able to understand some things. This VGS minus VT is called as VOB, that is excess VGS over VT, okay, or over voltage. And if you see carefully here, in let us say this particular figure, so what is this voltage? Where it starts getting flat. ID starts getting flat at certain voltage. What is that voltage? That voltage is nothing but VGS minus VT. Yes, I understand that VGS is a term which is at the input and VT is something else. But this particular thing starts happening at VGS minus VT. So if you see carefully, I'll do away with this stuff. So if you see carefully, saturation has started occurring here when VGS was 3 volt. Nearly that. It has started appearing here when it was 4 volts, when VGS was 4 volts. Here it was, let us say 3 volts. And then started here, started here, started here. If you look at the numerical values of these points, what do you see is that they are nothing but VGS minus VT. Or in simple plain words, when VDS is equal to VGS minus VT, that flattening has started occurring for different values of VGS. समझ में आ रहा है कि नहीं आ रहा है गाइस?
Yes, sir.
समझो अभी VDS मेरा VGS है 3 वोल्ट्स, ये डिवाइस का VT है 2 वोल्ट. तो VDS जहां पे फ्लैटनिंग चालू होगा, पिंच ऑफ होगा, वो वैल्यू क्या है? VGS minus VT, which is equal to 1 volt. So let us see whether we are having that kind of thing. So here, as you can see, you see that at 1 volt, it has started, pinch off effect has started. समझ में आ रहा है कि नहीं आ रहा है?
Yes, sir.
कि समझो for VGS equal to 4 volts, वो pinch off कहाँ पे होगा? Pinch off voltage कहाँ पे होगा? When VDS, what will be the value of VDS? There,
2.
pinch off
The 2.
4 volt minus 2 volt, that is 2 volts. So it will start happening at 2 volts. दिख रहा है?
Yes, sir.
Similarly, it will go on following the same kind of principle. So that particular voltage, in fact, it is the pinch off voltage, is simply called as the over voltage. VOV, at which the pinch off has started happening. ये बात समझो. So I can draw another curve to explain it in a better way in terms of the over voltage now. ये देखो अभी. So I am drawing just one curve, just one curve, और उसका nature देखो कैसे है. There is a triode region and then it starts flattening. It starts flattening at VOV. At the back of the mind, VOV is VGS minus VT. ये जो blue curve है, ये cut off region का curve है, where your VGS is less than VT. समझ में आ रहा है? So we are
So
talking
blue region कौन सा?
Sorry?
So blue region कौन सा?
ये ब्लू लाइन बोल रहा हूं मैं. ये ब्लू लाइन है ना, ये ब्लू लाइन है ना. let me highlight it for you with some color. ये रीजन में ये लाइन है ना, ब्लू लाइन.
Yes.
ये क्या है? When your VGS is less than VT, in fact that is when there is no drain current or the device is completely off. There is no induced channel. ये उसका कट
Yes,
ऑफ
sir.
है. समझ में आया?
Yes, sir.
Okay. So understand this carefully. It is very interesting. So to summarize, there is something called as so we have let us summarize it. Again, a few things that you have to understand. What will be if you look at this curve itself, what will be the output resistance? Output resistance क्या होगा? Drain resistance क्या होगा? Almost flat है तो infinite होगा ideally, है ना? ये रीजन देखो.
Yes, sir.
ऑलमोस्ट फ्लैट है. यहाँ पे इनफाइनाइट रेजिस्टेंस हो. अगर इसकी बात की जाए, ये रीजन की बात की जाए, तो यहाँ पे क्या है? जस्ट लाइक ओमिक रीजन इन केस ऑफ द जेफेट, है ना? तो यहाँ पे इट इज ऑलमोस्ट लीनियर, लेट अस से. So it acts as a resistor, voltage controlled resistor. दूसरा मैंने अगर कर्व दूसरा if I change VGS, then I'll have another curve. समझो ये है ना. इस पर अनदर VGS और इसका स्लोप अलग है देखो. इसका स्लोप अलग है. Just like what we discussed for JFET, same thing is here. So in this region, which is the triode region, it acts as if it is a voltage controlled resistor. All right. Okay, let us summarize now. So for VGS less than VT, so ID equal to 0. Second, VGS, which is equal to, let us say, VOV plus VT. ये कहां से आया भाई? Because we know VOV is VGS minus VT, na? So here a channel,
Yes, sir.
is induced and transistor, that is E or E MOSFET, operates in triode region or saturation region, depending on value of your VOV. Depending on whether channel is continuous so when channel is continuous, it is in the triode region or pinched off at the drain end. So if it is the channel is continuous, it will be in the triode region, and if it is pinch off, it is in pinch off at the drain end, it will be in the saturation region. ये बात समझ. Putting it in a slightly better way, so you have triode region and you have the saturation region. So continuous channel obtained by VGD or VDG, if you like, greater than VT, or VDS less than VOV. Any terminology you can use. Saturation region, you have the pinch off obtained by what? VGD less than or equal to VT, or you can call it as VDS is greater than or equal to VOV. ये बात समझ. Don't consider this. ये बात समझ. This we have already seen. And in this region, the characteristics, the equations are different. The equations in triode region, in that case ID, can be given as K into VGS minus VT into VDS minus half VDS square. ये उसका equation है. Or you can also write it as ID. In terms of VOV, we can write K into VOV minus half VDS, the entire thing into VDS. This is very, very important equation. Remember, this equation is valid when the device is in the triode region. Now let us see what kind of equation we have for drain current in the saturation region. So in saturation region, you have ID as K into VGS minus VT bracket square. Or you have ID as K into VOV square. Anything. Now this K many times is given in terms of some different parameters, and it is, so K happens to be half K dash into W by L. Now don't get confused. So what is this W by L? What is this K dash? So this K dash is also called as, so K dash is equal to mu n into COX. This deserves an explanation. Let me explain it. Okay. So if you look at the construction again, just a moment. Let me pull another nice figure. Just a moment, please. Okay. All right. Here is the figure. This is how it is constructed. We have just seen the cross section, side view. This is actually how it is in 3D. All right. So this thickness of this SiO2, now this SiO2, this particular system, that is the metal, insulator and semiconductor, this forms some kind of a capacitance. We already have seen that. And this capacitance is called as COX. All right. This capacitance is called as COX. Its thickness is also called as TOX, the thickness of this SiO2 layer. Now this distance between the source region and the end region is called as the length L, and the width is like this of this transistor. So this is the width. So this K dash is mu n into COX. Mu n is the mobility of the electron. If it is n channel device, if it is p channel device, it will be mu p. That is factor. Hello guys, am I audible? Hello.
Yes, sir.
So this K decides a lot of. This is a very important factor. Okay. It decides the characteristics of the device itself. So what you can see very nicely over here is that the geometry of the device decides its characteristics. This is what is wonderful. And that is the reason why your eMOSFET is become very, very famous. In almost all your devices, integrated circuits, your CMOS or your MOS device, that is the MOSFET, has dominated the integrated circuit industry. Okay? Why? Because the characteristics can be decided by the geometry of the device, the width, the L, length. Okay? So it becomes very easy to manufacture that way as compared to the bipolar junction transistor. This is one very, very important reason why eMOSFET or MOSFETs basically become very famous. And your MOSFET now is the basic building block of almost all your devices. Though bipolar junction technology is not obsolete, but still this has got several other advantages also, like the power consumption is less. Then, as you can see, that the input impedance is very, very high. Okay, which is actually a very good uh, requirement. All right. So again, as you can see, the MOSFET can be used as a switch. If I want to use it as a switch, I will put it either in this region to make it on, and otherwise I'll put it here to make it off. So two regions. I can operate it in two regions. This is where it will be on. This is where it will be. So this is where it will be on. The device will be on. Here it will be completely off. So I can use the device as a switch. And if I want to use it as an amplifier, I'll be making use of this saturation region. All right. Is that clear?
Yes, sir.
Okay. So with that, we finished with your fourth unit. We will start with the fifth unit from the next lecture. All right. I've tried to be very simple because MOSFET is not that simple, but I have tried to give you the simplest possible understanding of the MOSFET. Of course, I cannot. I cannot comprehend it for you. That is what is you're supposed to do. But start reading the books which are recommended by me in the syllabus also. So, any doubts, any questions up to this point? Hello.
No, sir. No
Okay.
doubts, no doubts.
Okay, then I will end the meeting here. Stop recording.